Good morning, ladies and gentlemen. Hope you guys are all doing well today. Today we are going to be looking at Kepler's Law of Planetary Motion. Today's video is super short. As you can see by the little icon at the bottom here, it is 2 pages and the first page is a meme. Couldn't help it. I need to plug in the writing tablet again. Okay, it seems to be like a morning routine, a Monday morning routine when I make my videos on Mondays. Oh yeah, plug in all the tech. Okay, so this video, ladies and gentlemen, is, as far as curricular objectives go during COVID, small potatoes. So we're not going to be spending a ton of time with it. This video today is super short. And I think I even took all the questions of Kepler off of the assignment as well. So this video is more for your education and interest and in case you see it again, but we're not going to see it again in Physics 30. So, but we're still running the video because we can. It's good for you. Learning is never wasted, ladies and gentlemen. So I hope you enjoyed the meme. For those of you guys who are Queen fans, you'll see the reference to Bohemian Rhapsody. Yeah, great song. Great song. Good movie, too. They did a very good job with that movie. All right. So, ladies and gentlemen, Kepler's Law of Planetary Motion. So, Kepler, cool guy, awesome scientist, he developed 3 laws of planetary motion. And he based this based off of his observations and math. So what he observed is that the planets move around the sun in elliptical orbits. And the sun is what is called the center or focus of the ellipse. Now, the thing is that an ellipse is not a circle. It's a fancy name for an oval. Okay? So planets do not orbit the sun perfectly circular. Okay? And that, notice these are very, very slight differences here. Okay? The sun's the center of their focus of that ellipse. Okay, that's law number 1. Law number 2. This one's a little bit trickier, ladies and gentlemen. And if you connect a straight line joining the sun and a given planet sweeps out in equal areas and equal time intervals. Now that sounds really awkward. Let's put this in real terms instead of sweeps. Okay, we got a planet here. Okay, the planet will move as time goes along to this point here. Okay, so this X point to that X point. Maybe switch to blue. It might be easier to see against the pink. There you go. Okay, and then you draw a line from where the planet is at any given point in its orbit. Draw that line to the sun. Then the time is going to, the planet's going to move for, I don't know, give a period of time. Let's say 7 weeks. Why not? Random number. And during that 7 weeks, the planet will move to here. Draw a line to the sun from that point. Okay. Now, because the orbit's an ellipse, the distance from here to here is going to be different from here to here if this point is also 7 weeks. Okay. So because of the weird shape of the orbit not being a circle, here to here is 7 weeks. Here to here is 7 weeks. We'll draw a line from where it started to the sun. Draw a line to where it started 7 weeks later. If we were to calculate the area of this shape and the area of this shape, it's going to be the same. Okay? And it's due to the fact that the planet's going to be moving at different speeds during the orbit depending on its radius. And we'll be looking at the math of that a little bit later. So, yeah, so that's Kepler's second law. Don't worry, you don't have to do any math on that one. Heck, even during COVID, I think I gave like 1 multiple choice question on the unit test, and it was a theory question. So don't panic too much on that one. Better yet, just don't panic. Panic isn't good for you guys. Okay. So, ladies and gentlemen, next piece here, this is the part which is the most commonly used aspect. If we weren't in COVID, I'd put put a question like this on your assignment or something. The ratio of a planet's orbital period squared to its orbital radius cubed is constant. So essentially, K is what is called Kepler's constant. So if you take the period of any object that is orbiting, say, our sun, square that, and then take the radius, cube that, divide them, you're going to get the same value. The key piece is that they have to have the same focus. So that would mean that Earth, Mars, Jupiter, Pluto, poor Pluto, no longer a planet. Tear. Pluto will always be a planet in my heart. When I was a kid, it was still a planet. I don't remember when it was changed into no longer a planet, but I don't know, but it was a while ago. Okay. So ladies and gentlemen, however, our moon is not orbiting the sun. Our moon's orbiting Earth. So that means that our moon and any of the other artificial satellites that are spinning around our planet, like for GPS, for example, or satellite TV, you name it, all of those guys will have the same value, the same Kepler's constant. Okay? So, ladies and gentlemen, this is another way that you could word this here. Okay? So, you could rewrite this, if we take this r cubed and multiply it over here, r cubed times the constant is equal to the period squared. So, we could say the square of the period is going to be directly proportional to the cube of its mean, so average distance from the sun. So we could write it as r cubed is proportional to t squared, so directly proportional. Okay, so ladies and gentlemen, so that is essentially Kepler's third law there. And he was able to describe how planets move from these observations, and Newton was able to describe why they move. And in our next video, that's what we're going to be looking at, is Newton describing why they move. So here's some practice problems for you guys. If you feel like doing those, if I was you, I wouldn't do them because this is on Kepler, and I've yanked all the Kepler questions off your assignment. So don't do any of those right now. If you feel like it, you can, but I wouldn't. Okay, save them for orbital dynamics. And yes, if you guys are wondering, I am wearing the same dress that Dr. Hinshaw has. Couldn't help it, had to buy it. I saw it years ago and was desperate to buy this dress. They were sold out. Dr. Hinshaw, styling woman, brought the trend back. All right, anyway, ladies and gentlemen, hope you guys are having a good day, and we will talk to you all later. No fires, injuries, or explosions. And now I can't turn off the video again. This seems to be like a daily event. It's like not being able to get the smartboard to talk to the computer. All right, guys, have a good day. Bye.